The combination of simple functions which we are now interested in being able to integrate are products, two of the simple functions from our table multiplied together. Again, this situation is generally very difficult to solve, but there are some cases where we have the tool to solve it. The tool we will use is called integration by parts. This is the integration by parts formula. To explain how we use it, I want to bring back the idea of the function ladder from the first video. A function on the ladder moves down a step when it is differentiated and up a step when it is integrated. Imagine the ladder for each of the functions in the product. We will call one u and one v. The integration by parts formula says that if we identify one of these functions as being on a level lower than the other, let's say we have u and dv dx, we can relate the integral of this product to the integral of the product of functions when we swap positions on the ladder to v and du dx. The integrals are close to being the same as each other, but we get a byproduct when we switch the positions on the ladder. The byproduct is in fact given by u times v, the higher level for each of the functions multiplied together. This is outside of the integral and so poses no problems. Why is this technique useful? We hope that switching the positions on the ladder results in an integral that is simpler than it was before. One example of this is when one of the two functions is a linear function. If we identify the linear function as being on the higher level, bringing it down to the lower level gets rid of all of the x terms and just leaves a constant. This new product is much easier to integrate. In fact, if one of the functions is a polynomial at all, we can always do integration by parts to move it to a lower order polynomial. It may not leave us with a doable integral straight away, but we can repeat the process to move the polynomial lower down and down the ladder until it is just a constant, at which point the remaining integral will be solvable. We must be very careful to include the byproduct term each time we do the integration by parts. One case where integration by parts is useful is illustrated by the following example. Let's say we are finding I, the result of the integral e to the x sine x, and we identify sine x as being on the higher ladder level and e to the x as being on the lower. We find du dx and v and apply the by parts formula to relate this integral to the new one. This new integral looks just as complicated as the first, and we also have this byproduct term now, so what have we gained? Well, if we apply the by parts formula again to this integral, this time saying that cos is on the higher ladder level, we find the missing pieces and get the following result. The remaining integral now looks exactly the same as what we started with, and it is equal to what we defined as I in the first place. Since we are looking for I, we can sub it in for this integral and simply rearrange to write what I is. We have avoided doing the integral altogether. This worked because integrating the product twice by parts resulted in the same integral that we started with.